Okay, I think we will start. Hi everyone, I'm Shachar Kvatinsky from the Technion. I'm heading the ACRC, and as part of our webinar series, we are happy to have Bernhard Wicht today that will talk about power management. This is a part of a series of webinars. Our schedule is completely full until June, so stay tuned to the announcements that we will soon have about the next webinars. So we are very happy to have Bernhard Wicht from Leibniz University in Hannover. Bernhard, thank you. Just make sure that you unmute yourself.
I would think you can all hear me.
Yes.
So, Shahar, thank you very much for the introduction and welcome to this talk on my favorite topic on power management. And before we start, I would like to express that it's really my pleasure and also my honor to give this talk today. Of course, I regret that I can't be present in person, but maybe we do that at a later point in time. I also have to express my gratitude to a few people who organized the whole thing. So this talk, which is Masha Schuster from the Advanced Circuit Research Center, who organized this since a couple of weeks. And I'm really grateful. Thanks for this, setting everything up. Then I also have to thank Solon Spiegel, who is representing the Solid State Circuit Society of the IEEE in Israel, who made this connection to the IEEE. And finally, I have to thank Claudio Jacobson, who initialized the whole thing after we met back in February at ISSCC in San Francisco. And that was almost the last point in time when we could freely travel. So it was really a nice coincidence. And based on that, we set up this talk today. So with that, let me start. I would also encourage you, if anything comes up, please raise your hand or speak up so that you don't miss anything because of technical issues, right? So then let me first introduce my university. Just to give you a little bit of a background, I am with the university in Hannover, which is more in the north of Germany. And it's one of the large traditional engineering schools in Germany, which is named after Gottfried Wilhelm Leibniz, who lived roughly 300 years ago. And he spent most of his life in Hannover. And what I feel is really fascinating is in his handwritten documents, he already sketched like 300 years ago the binary code scheme, as you can see here at the bottom. And part of that became the logo of the university. So you see that here also on this slide. And just to name a few particular connections here at our university. So Hannover is very close to the headquarters of VW. And also Continental is headquartered here out of Hannover. And also smaller companies like Sennheiser, the acoustics audio company, is from Hannover. And last but not least, also maybe even more important, this cookie and chocolate factory is Basen is also based here in Hannover. So with that, I think you're all working in circuits, so I probably don't need to show you this introductory slide, but this, the intention is also to share this excitement on circuits, in particular on power management, with all of you. So if we take all these electronics components and put them all together, we can put together this scheme for microelectronic systems, how it is hooked up to the environment. So the environment has a lot of analog quantities, including temperature, pressure, speed, acceleration, or light intensity. And from that, we detect all these quantities by our electronic system. That could be a module, can be a PCB, or it can be a microchip. And usually we have very small sensitive signals that need some kind of signal conditioning, noise reduction and preamplification until we go into our electronics, and eventually we convert from the analog to the digital domain to do digital signal processing. Now, if we, out of this signal processing, want to take influence on the environment again, to close this whole loop here, we go back from the digital to the analog domain, and then finally activate either some simple thing like a LED, a warning lamp, relay, or we drive actuators like switches, solenoids, or motors. And in addition, all these circuit blocks need to be supplied. So we need some kind of power management, and that altogether forms the topic of today's talk. It includes power management in general, and in particular, of course, also some kind of actuators, drivers, and so on. From a top-level view, power management basically bridges the energy sources, and we will talk about that in a few seconds more in detail, to our particular electronics. So what we see here is that during the operation, our electronics sees a fluctuating load current. It sees some varying voltage levels. So the power management has to deliver the appropriate power and voltages at a maximum efficiency out of the energy source. And this power management can be implemented as part of complex ICs, either or as a dedicated power management IC, which is really a growing class of products, which usually is referred to the short-term PMIC, right? And so this is a little bit what we will talk about during this talk. Let's start with an example. So we all use mobile communication, smartphones, and in fact, we are nowadays facing roughly the 30th anniversary of the introduction of mobile phones. In preparation of this talk, I looked it up in Israel. It started also about 1991, and I think in Germany 92, around that time. So, and it started with very heavy and bulky phones like this one here, which could only make phone calls. That was the only function. It was quite heavy, 500 grams. And the standby time was barely 1 day, actually much shorter. And so there was a business model actually to sell an additional battery pack, which doubled the weight and expanded your standby time a little bit more. So, and usually if you would be in the same room, I would ask you, what do you think was the cost of this first mobile phone? This is the official name was Motorola 3200. I give this answer right away. So it was 1,500 euros. So this is a lot, given the fact that this only could make phone calls and nothing else. And it nicely shows what we achieved by progress by microelectronics. If you look at today's smartphones, making phone calls is one of the few functions in addition to all the other things that we can do. The phone is very lightweighted. And of course, we all complain still that the standby time is not sufficient, but it's of course much better, especially given all the functions that we can address with it. And in summary, this is achieved by really low power electronics and also by dedicated power management circuits. So now we do what we usually don't want to do with our expensive smartphone. We drop it so that we get the electronics visible that is inside the phone. And I'm taking here the iPhone 10 electronics, a part of it. In fact, we see here at the top side of this PCB already 4 power management ICs. And we also see on the back side, if you would turn it, then on the back side, we would see another three ICs which are power dedicated. that also includes ICs for the power amplifier or wireless charging and so on. So if we look a little bit closer, and I hope that is really visible through all the online connection, around the IC, we see a lot of discrete components. Actually, the whole PCB is fully filled with C and L components. And they already got smaller over the years if you compare to the iPad of the first generation, which is shown here on the right-hand side. Of course, it's different power classes. So the iPhone is roughly 1 watt, while the iPad is more like 3 watts of power. But still, you see that the discrete components here are much larger compared to what we see here. And the trend continues. One of the goals in power electronics and power management in particular is to get rid of these components, these discrete components. On the other hand, they will physically be still there. We need them, and we will talk about this in a few minutes. But there will be, when they get smaller, we can co-integrate them in the package, in the same package, or have even on silicon integration of these passive components. So that's the goal. In the end, we don't know which way it will be done, but it will happen. I'm pretty sure we will see that in a couple of years. If you look at one of the electronics in the future, there will be only chips that are visible. In the end, it's cost driven. Also, this will be a topic we talk about. On the right-hand side here in the lower right, I show a solution out of the automotive space, which nicely illustrates power electronics. So it's a motor control IC built in a module for the conventional combustion engine. And this has the idea to, or the purpose to deliver the right torque that the driver requests, while keeping the emissions and the fuel consumptions at a minimum. So in all these metallization here on top shows that it's thick copper metallization, which allows to drive large currents across the die. So to come back to our scheme for power management, we now see some more key requirements. The major point is the solution size. It applies to a lot of microelectronics, but in particular to power management. Nobody wants to see it. So that's why we see the size, volume as key requirement. Footprint should be almost 0. This is one of the requirements. We want to use the energy source to 100%, so efficiency matters as well. And finally, we want to be reliable. We have some switching operations, so we don't want to have disturbances. We need to fight with EMC issues and so on. So this is one of the additional requirements. And in the end, nobody wants to pay for it. We know that very well in a lot of electronics. This is what we are facing. So that doesn't look so good. But on the other hand, I tell you, it's a lot of fun. And that's what I want to show a little bit in the upcoming slides. Let's start with a very simple, easy example. If we want to convert from 12 volts to 2 volts, it could be, for example, the car battery of a conventional 12-volt board net, and we want to convert to 2 volts to supply maybe a microcontroller. So the very simple thing, very, very simple thing could be to use a resistor. So we have our 12 volts input source. We want to convert to 2 volts. Our load current is 1 amp. So we get a voltage drop across the resistor of 10 volts. And in the end, it works that we get 2 volts at the output. However, we all know there is a lot of power dissipation. Just for the resistor, we have 10 volts across. 1 amp gives us 10 watts of losses here, which is even larger than the output power, which is 2 watts. So this sounds a little bit strange, but this is a very common concept, which is the linear voltage regulator. And this is by far the most established voltage conversion concept that we see in nowadays electronics. So in the end, in the real application, of course, we would not use a resistor. We would place a transistor here and we would adjust its voltage drop. by a control loop so that we get the proper voltage at the output. So if there wasn't all the power losses here, we could stop my talk here at this point, because there is nothing better in terms of voltage quality at the output. So the linear regulator would do a great job, but since we lose so much power and efficiency here, we need to think of different ways to implement it, and that brings us to switch mode conversion. Again, let's look at our example. We convert 12 volts to 2 volts and use switches. This is our input voltage source, 12 volts. And these switches here now are alternately turned on, so that when we turn on the switch 1 here at the upper side, we bring energy into the system. And now we have a discrete filter placed here, a low-pass filter made of L and C, which has actually two functions. One is energy storing. While the switches are not connected to the energy source, the energy is delivered out of these L and C components. And the second function is low-pass filtering. It happens as follows. Due to the switching, we get some pulsing switching node waveform. And now our low-pass filter builds the average so that we get the appropriate DC voltage at the output. And now, since by changing the on time of the pulses at the switching node, we can basically control the output voltage level. So that works quite nicely. And now let's look at the losses. If our switch, first of all, let's look at the ideal case. So a switch has these two states, of course, on and off, and in both states we get zero power losses. So if the switch is off, we have zero current flowing, and if the switch is on, neglecting its on resistance, we have zero voltage across, which also corresponds to zero power loss. So that has quite a large potential to convert voltages with high efficiency. And this is what we see in a lot of applications nowadays. We can achieve power efficiencies higher than 90%. This is the concept which is implemented in switch mode power supplies, so to name this term. And in the end, we use pulse width modulation to control the output voltage in a control loop. And that's not only applicable to medium and low power in our ICs, it can also, or it is also installed and used in power plants for gigawatt of power conversion. So that's quite interesting. And now let's look in how we use those concepts to supply various electronics. The idea is to install these regulators locally at the various electronic blocks with dedicated voltages. And that's called point of load conversion, because it's directly, every load gets directly at the point of load the appropriate power management circuits. And so we can supply various blocks, microcontrollers, microprocessor cores, DSPs, analog and digital circuitry, mixed signal circuitry as well. So for instance, here in this case, we have a portable application. We run it from a lithium-ion battery around 3.8 volt nominal voltage. And we have now a cascaded approach of a switch mode converter. This is the buck converter here, a step-down converter. And from that, we run a linear regulator. That's actually quite common to the high-efficient switch mode converter, brings down the majority of voltage, so that we see only a low voltage drop across the linear regulator, so that this thing operates at high efficiency while it still maintains a very clean voltage. I didn't mention that a minute before when we talked about switch mode conversion. The output voltage had some little ripple, which is due to the switching nature of this switch mode conversion. So, and by a subsequent linear regulator, we get a very clean supply, which is then very suitable to supply various electronic blocks. Overall, this example here shows moderate conversion ratios. We basically convert from 4 volts to half of it to 2 volts roughly, which is a little bit different if you look at high voltage applications such as automotive, industrial, or even IT servers. So here this example has a car battery, nominal 12 or 14 volts, and then we see across various cases a lowest voltage of 4 up to 40 or higher voltage. So, and that's now again tied to some linear regulators, switch mode regulators to supply the various electronics. And so this has much higher conversion ratios, right? We have roughly 10 to 1 to convert from 50 to 5 volts and so on. So just to name this as an example a little bit. So what else is important now? Let's look at the energy side, at the system side, which I've added to the scheme for power management in this slide. So there are various applications which have different voltage levels. So it starts with energy harvesting, where we get millivolts of supply voltage up to a little bit higher voltages, depends on what kind of harvesting concept you use. While this 30 volt would be rather for vibration harvesting, while we see millivolts for light and so on, and RF harvesting maybe. Then we go to higher levels with low voltage batteries. We also reach topics like USB or e-bikes, and nowadays also drones are very interesting with a little bit higher supply. And I also would like to highlight automotive. So with the trend to electrical cars, we get a high voltage board net, which is roughly 400 volts, in addition to the conventional 12 volt net. And we get nowadays an additional board net, which is 48 volts. Interestingly, it's similar for IT servers. So like Google data centers, they run from an intermediate voltage of 48 volts. And this is all because you want to get your losses to a minimum. So, and this also indicates we have a trend to higher voltages towards 50 volts and higher on the application side. And now our power management IC bridges the link to our electronics, which actually sees a trend to lower voltages. We all know, of course, core voltages of digital electronics goes towards 1 volt roughly. And this is again for power reasons. We also see a increasing load range from standby, which is roughly a few milliamps or even microamps of power, towards fully operational power drivers, motor drivers, and so on, where we see 1 amp of load and even more. So this is also to be addressed by our power management solutions. So, and as we see here, there is a trend towards higher voltages. In my team, we have started to do some research in that area, which, for instance, covers a conversion from 48 volts in automotive or data centers to below 5 volts. And if you look at a state-of-the-art implementation of electronics, it's interesting to look at this photograph here. This shows that our IC of the switch mode converter is actually quite small, while the passive components are huge. This is the inductor that we place external, and this corresponds to a switching frequency of roughly 1 megahertz, which is more or less state of the art. And now, if we now increase the switching frequency, we simply go to smaller times for energy storing. That means our storing components, L and C, get smaller if you run at faster frequencies. That's the goal. And so we go perhaps towards 100 megahertz, which ends up with such a small passive size that we eventually can integrate it into the package or on the die even And this is the trend. You may remember the smartphone electronics picture with all the little discrete components around. This is what we want to address here. Now it sounds straightforward, but it is not that easy, and there are several challenges to why we are not at 100 megahertz in most applications yet. And this is what I want to highlight here on this slide. So there are basically three main challenges for fast switching converters, in particular if voltage, input voltages are increasing. So the first one is in fact the losses themselves. We have, when we looked at the switch mode concept, we've seen that there is, these switches have their two DC states on and off, and they have basically no losses in these states. However, during the switching transition from on to off and vice versa, we see that here in this little graph, we have a current, which is green, and red, the drain source voltage of the transistor. They are non-zero at the same time. So in the end, we get some losses, which corresponds to that loss triangle here. And unfortunately, these losses, they scale with frequency. So if you want to go to higher frequencies, the losses increase extremely, and we need to address it. And so two concepts can be used, they are quite useful. The first one is soft switching. And the second one is dead time control, which I will address in a few seconds. Let's first look at the second reason why we cannot easily increase switching frequency so significantly. The second reason is speed. So if we have a little bit higher voltages, we need to use dedicated technologies, and they are not optimized for fast switching. Let's take a look at the switching node again. If you zoom in here and take, for example, a switching frequency of 30 megahertz, and we do a 10-to-1 conversion, our on time calculates to roughly 3 nanoseconds. In order to get a pulse width modulation, so a pulse, our edges rising and fall time need to be below 1 nanosecond. So, and this sees the full swing of maybe 50 volts. So that's a challenge. It's really steep and it's really fast. And that's why we have challenges on the circuit side, for instance, in the area of gate drivers and level shifters. In particular, so on the circuit side, but there's also work done on the technology side to speed up these power technologies. And with these switching, steep switching edges, you can imagine that there's at the same time already some issue in terms of coupling. And in fact, that's also limiting ourselves. We have seen that in my own group, when we implemented these kind of high voltage fast switching circuits, we saw a lot of coupling effects, which comes from substrate coupling. We also see, of course, it's switching, we see EMC noise. That can even cause malfunction of analog circuits, but also digital circuits. So you may even get bit flips in your circuits. And there's various ways to address this. It includes, of course, proper assembly, short lines, low parasitic inductances, isolation options on technology side. Trench isolation helps, of course, a lot. Also, what we have investigated here in this little graph is backside metallization. So BSM means backside metallization. So our back-grinded die gets a conducting layer on the backside to suck away any substrate currents right away. And that also minimizes the substrate coupling and debiasing immediately. On the noise source, we can implement slew rate control. That means our switching transition will not be as steep as possible. It can be adjusted depending on the operating conditions. And finally, if we go to what is called resonant operation, we may get sinusoidal transitions instead of these hard switching waveforms, which also decrease decoupling and improve EMC issues. So with that all together, we can take a look at these two basic concepts that help us here. First one is soft switching, and the second one is daytime control, which we will take a look at in a second. So first of all, soft switching. There are various ways to implement soft switching. The most beneficial and most common one is so-called zero voltage switching. What does it mean? We see here, we see a power stage of a switch mode converter, again with the LC filter towards the output. And now let's take a look at the switching node. If we turn on our transistor, the transistor in the conventional way, which we call hot switching, sees the full V-in transition across the transistor, and that's causing switching losses. We have seen that before with this loss triangle, but it also causes capacitive charging losses applied to all the capacitances that are present at our switching node, and that's a lot. And this way, we already scale our switching losses with frequency, but also with input voltage. And it can be nicely seen in this diagram here. So the voltage, the x-axis shows the voltage, and the losses corresponding to the input voltage increase significantly, as we can see here, right? And now, and that's already at quite fast switching at 10 megahertz. So what can we do about it? Now, the idea for soft switching is to bring up the voltage before we turn on our transistor. I'm illustrating that here by this graph here. So if we achieve that, we do not see these capacitive switching losses. We also do not have switching losses within the transistor because current and voltage are not non-zero at the same time. So and that has significant influence on all the losses. It brings it down to very low values. So then with these concepts, it's possible to really go to higher voltages and higher switching frequencies. How can we achieve that? One common concept is to implement resonant conversion concepts based on an additional LC tank which resonates. We have one circuit here on that slide. That's we call that concept parallel resonant converter. Again, we identify here our conventional buck converter, which consists of this high side switch, the LC component here, the LC filter, plus this one here is the freewheeling diode, which we have placed here instead of the low side switch to keep things simple. So we again see a pulsing waveform at the switching node, which is displayed here over time. And now what did we do? We added a resonance circuit directly to the switching node, which consists again of an inductor and a capacitor. So this is the CR-LR plus another high side switch. And now how does the whole thing work? The output regulation is, as before, maintained by pulse width modulation. So the turn on time of this main transistor determines our output voltage. As in the conventional way, there's no difference compared to any buck converter that we have seen before. Now, the resonance circuit operates in that way that the on time of the resonant transistor allows to bring energy into the switching node, and so that the switching node voltage rises up. And now the on time of the second transistor controls the amplitude of our switching node exactly when we turn on, or if we turn on our main switch. And this way we can control zero voltage switching of the main switch. So the on time of the second transistor easily controls the zero voltage switching at the main switch. And that needs to be controlled by a control loop because over varying operating conditions, load current changes, input voltage changes, and so on, we see different resonating behavior here. And there's one third point. Of course, we add another transistor here, which basically sees the similar currents as the load current. We may also get switching losses here. And now the trick is to achieve zero voltage switching at that transistor as well. And in order to do so, we have implemented a capacitor array here. So this cap array is a binary weighted cap array, which can be adjusted. And if that is properly set, we also achieve soft switching at the resonance circuit and at the second switch. So these are the three main benefits we get here from soft switching in this implementation. And maybe one little side info, this is a P-type device, which is usually not preferred for power since it has a lower on resistance. That was technology related that we had to use a P-type device because this node swings to large negative voltages if it's in resonance, and that needs to be supported. And here we had to use the P-type device just as a side information. All right, so this is the first concept which is very beneficial in power management. It's called soft switching and zero voltage switching in particular. The second concept is dead time control. The ideas now, maybe look at the power stage first. Again, here we see now our LC, low pass filter, and high side switch once more. And now we have replaced our low side diode. If you remember the slide before, we replaced it by a real transistor, which is beneficial since the voltage drop across can be very small if we size the transistor properly. The drawback is that we need to control it separately by a dedicated gate driver and control circuitry. However, as this is interesting to achieve good efficiency, we have a bridge configuration, and we need to really make sure that there is no cross current. In either case, we have low resistive switches, and cross currents could really cause some damage due to cross conduction. So we want to avoid that. On the other hand, there's also losses associated with the dead time. So if the dead time is too long, we see body diode conduction of the low side device. So it's indicated here by this red diode. There is, first of all, a forward voltage. Always, as long as we have a dead time here, it's a little bit illustrated here in that graph. So the diode conducts with the roughly 0.7 volts across, in addition to the full load current that flows across the diode. So there is some losses. And we also have losses corresponding to the reverse recovery effect of this diode once it turns back into blocking mode if the switching node goes to higher levels. So there's quite significant losses, and that requires dead time control. So there is, of course, it can't be zero, that's clear, to avoid cross conduction, but it can't be too long, otherwise we get too many losses. Unfortunately, the proper dead time depends on the operating conditions, and so we really need to have some control in place to set the dead time properly. And there's even one more nice feature. If we set the correct dead time, we may even achieve zero voltage switching because we use a little bit of our inductor current, output current, to charge our switching node either to zero to achieve zero voltage switching across the low side switch here, or we let it swing up to V in to again have zero voltage across the high side device. So all in all, we have roughly 25 or 30% loss reduction potential by proper dead time control. And that's what we have investigated in one of our projects. And I would like to show you one example here, how that can be implemented. This is a so-called predictive mixed signal dead time control. Predictive because it looks cycle by cycle. Was the dead time set properly? And if not, it will be adjusted for the next cycle. So briefly, how does it work? So again, here we identify our half bridge, our power stage. There would be the L and C low pass filter connected, which I've omitted here for simplicity. And now we sample the switching node voltage in an analog sample and hold circuit exactly at the turn on instant of our low side switch. So, and that has a lot of benefits. The sample and hold circuit is shown here. First of all, we have implemented here a resistive or an RC voltage divider to bring our high voltage of the switching node, which can swing, for instance, to 50 volts here at the input. We bring it down to the low voltage domain to hook it up to the sample and hold stage. And then, so we have implemented roughly 10:1, but this is not so critical. So it's, and then we store our voltage at an analog sample and hold stage at capacitor. And we actually use 2 stages here to relax the speed requirements, such that we have the full switching period available to do the assessment. Is our switching node voltage within a small window around 0, or is it below or higher than the threshold? And that's detected by a window comparator. And if we are not within the window, we increase or decrease a counter value. And that's fed into a delay line to set the dead time properly. So if you investigate the required dead time, you find there is a strong sensitivity towards the operating conditions, input voltage, load current, and so on. So we identified a minimum required dead time of 125 picoseconds, while the maximum is 32 nanoseconds. And that's why we had to use 8 bits of delay line here and counter to set our dead time across this large dead time range. So the dead time itself is set by a delay line which uses inverters. And what we do here, again, the technology didn't allow to set very small dead times because the propagation delay of 2 inverters, so to get a non-inverting logic propagation, is larger than 400 picoseconds. In order to get 125 picoseconds, we simply set up this delay line as a differential delay line with this delay line here at the bottom offset a little bit by an additional capacitor, which is actually another logic gate to achieve this delta of 125 picoseconds. So that's what we have implemented here. And one of the nice features is that we keep our switching node at 0 volts so that the body diode of the low side transistor does not turn on, which gives us additional benefits here in terms of efficiency and losses. So overall, we achieved 30% of loss reduction, which accounts to 6% higher efficiency at an operating frequency as fast as 10 megahertz. So this graph shows efficiency as a function of the load current up to half an amp, and this is quite nice, the improvement here. By the way, this paper was shown first at ACRC in 2015 and achieved the best paper award by my former PhD student Jürgen Wittmann. So that was really a successful implementation. These challenges that we have looked at for fast switching DC-DC converters also become visible if you plot the state of the art in such a diagram. It shows the efficiency as a function of the input voltage. And we have included here scientific publications, but also commercial products at various switching frequencies. This kind of graph shows that there is actually a solution for all different voltages with sufficient efficiencies. So from this graph, actually everything looks fine. However, if we now plot all these little data points in a different way, we plot the efficiency over frequency, switching frequency, then we can immediately identify that most of the parts operate at frequencies below 5 megahertz. And that's now really the state-of-the-art frequency. There's a few parts running at 10 megahertz, but that's already part of our own research. So we also identified when we talked about the challenges that a frequency of 30 megahertz is already a kind of a limit, which is due to the speed limits of the technology, as well as simply of the circuits that we need, like gate drivers, level shifters. So that shows us there is a gap in between. And these concepts that we just talked about, the dead time control and the soft switching, allowed us to a little bit cover that gap. So our dead time control concept runs at 10 megahertz, while our resonant converter even achieved 25 megahertz operation at a reasonable 70%, a little bit above 70% efficiency. So there is, besides inductive switch mode converters, there is different ways how to convert voltages. And this is interesting to look at as well. If you talk about power management in general, we see in this graph, we see a simple power stage consisting of switches and capacitors here. So it's a 2-to-1 step-down converter that we get from here. It's a two-phase system. So we have a clock phase phi 1 and phi 2. The equivalent circuit is such that we have a series connection of both capacitors, while and they are both connected to the input voltage. So the input voltage drops across both in series. And in the second phase, we put them both in parallel. And if we do that frequently, we reach a steady state voltage at the output, which is exactly half of the input voltage. And you may wonder, this is always surprising, if we have different values of capacitors, even then we get half of the voltage at the output. It's just if we have one cycle, the charge sharing, that's different if the capacitor values are not equal. So that has an influence, but the settled condition in steady state still indicates half of the voltage will be present at the output. This is because we put them in series and in parallel. So let's get back to our question. How can we convert now 12 volts to 2 volt by such a cell? We basically cascade multiple of these 2-to-1 cells, one after the other. So in our case, from 12 volt, the first cell would convert to 6 volts, and then the second one converts from 6 to 3 volts. Then we are at 3 volts. So now what are we gonna do about the 1 volt that is still missing? And that's in fact very interesting in this case. That points to this little term here at the end. What we do is we basically let the load current discharge our capacitance so that it drops from 3 volt to 2 volts. And that can be done by properly setting the amount of time that we let the current discharge our capacitances. And this can be achieved by modulating the clock frequency in the easiest case. And so, unfortunately, this last step causes some losses. And it could also be seen as an equivalent output resistance of this step-down converter. And that's, of course, lossy and but it allows us to come to exactly 2 volts out of 12 volts. So the key point is also here we see losses, and we need to have a little bit different control compared to inductive converters. But this concept is very interesting, has gained a lot of popularity over the last, I would say, 10 years. switch cap converters are interesting because they can be fully integrated on the die together with all your electronics to achieve point of load conversion and point of load power supplies for processor cores and so on. In our case, to show you one example, we have used this approach in a micro power supply, which was intended to eliminate bulky power supplies, discrete bulky power supplies that we all carry along, which are a little bit nasty. And our idea was to integrate everything on one IC. It would be also a nice alternative to energy harvesting. Imagine we have a building which has some sensor nodes which need to be supplied, and our idea was we just deliver one IC which has high voltage capability, and then we hook it up directly to the AC grid. So, and that's why we implemented a high voltage interface which down converts to 20 volts. Of course, that required to use a high voltage technology, and this is a 700 volts technology. And from this 20 volts, we used this switch cap converter concept to bring it down to 3.3 volts, which is perfectly suitable to supply our remaining functional electronics. The die itself is quite small, and in fact, our intention was to use no external components. It didn't work completely. We have one more external capacitor required to buffer our zero crossing of the AC voltage of the AC grid. Besides that, it's still quite small. And also on that die, we can see mainly there are capacitances implemented, as well as the switch matrix here for control. On the right, it's not so much indicated. There is the high voltage interface implemented. So that was actually quite nice as well. And there's a couple of publications. We showed it at ACRC 2016 and subsequent papers. And because we felt this is quite important to work in this area, the power was quite limited here in this application. It's a few milliwatts. We thought, how can we improve it? And that's why our new research is positioned in between discrete power modules, which are again larger and not optimized so much for low power efficiency, and in between energy harvesting, which usually suffers from low energy that is harvested, usually not sufficient to supply transceiver circuits and so on. So that was the idea. And this is a circuit that we presented at this year's ACRC back in February. It's a IC that does a one-step conversion from 325 volts down to 5 volts. Actually, we can support 3.3 to 10 volts so at the output. And that does it in one step. And it achieves still reasonable efficiencies of almost 80%. In order to get this implemented, we combine now inductive components and capacitive conversion concepts. So it's not purely a capacitive converter. And that's bringing me to the next way to convert voltages. Again, our question, 12-volt conversion to 2 volts. How to do that? Now, what we do here is we add to our switch cap matrix simply an inductor, such that the energy transfer from the flying capacitor here towards the output capacitor is connected by an inductor. And by doing so, we soft charge the capacitances, and that basically reduces our capacitive charging losses, but it also corresponds to a reduced output resistance, which then again reduces losses, and we simply achieve higher efficiencies compared to a purely capacitive converter. There's a drawback, of course. By adding this inductor, we increase the complexity. We see it here already, but if you imagine we implement a control loop, then it may get much more complex, of course. And but the good news is we are all in microelectronics, so complexity can be handled very well on microelectronics and circuit side. So this is very interesting, this class of converters. As the L and C forms a resonant tank, these concepts are sometimes called resonant conversion or resonant converters, or, which is also quite common nowadays, it's hybrid converters, because we use L and C as a hybrid converter concept. Also here, I would like to show you one example in the area of variables. So the target here was to implement a DC-DC converter for variables, which can be simple applications like fitness trackers, but we all know it's a very fast-growing industry sector, which also includes like biomedical monitoring appliances that need to be portable, so that it needs to be lightweighted and very small in size. So the strict requirement here is to really get solutions which do not need external passive components. And so that's why we investigated hybrid converter concepts. And that's in fact the IC here that does a power conversion from a lithium-ion battery, roughly 3.8 volts, down to an output voltage in between 1.3 to 1.8 volts. And the exciting thing is that we achieved that without any components by placing the passives on the die here. So this is the die, the IC, which again shows you nicely that these passives have some size. So they are capacitances. These are two flying capacitances. This is the output buffer capacitance in the nanofarads range, as well as a spiral inductor, which is 9 nanohenries. And this red color indicates already there is some thick copper layer on top, which allows us to get a good Q factor for the inductor, but there's no magnetics or anything. It's just the pure process as it is. And so this is a circuit that we introduced at ACRC 2019. It uses a matrix of switches and capacitances. I show that in the next slide. So here again our die, and then here the switching matrix consists of a lot of switches, 9 switches here and 2 flying capacitors. They drive our switching node, which again sees a varying voltage. In this case, it's a resonating voltage, so it's no hard switching pulses. It's sinusoidal shaped, and that's again filtered and buffered by this LC, as we have seen initially as well. Now this is really small. Again here, roughly 9 square millimeters. As these components on chip are relatively small in the nanoscale, we need to have short energy storing times, which means we need to run at very high frequencies, which is 47 megahertz maximum in our case. And so, but still we achieve 85% peak efficiency. And it's interesting to compare that as well to state of the art, which is so-called system and package solutions, which may look familiar if you remember our smartphone, where all the different discrete components were placed close to the IC. Here, the same here. Interestingly, these passives are in the micro range, so microfarads, microhenries. And that's because our switching frequency in these system and package solutions are in the lower megahertz range. We have seen that before. It fits very well. It's 1 to 5 megahertz. And since we need to place these external components, there's of course additional assembly cost and effort and issues related to it. So that's interesting to compare it. Let me summarize the state-of-the-art overview in this graph. I'm watching the time a little bit. So this graph, just shortly to show you, shows the power efficiency as a function of the load current. What we do here is we look at the minimum and maximum load current. And I wouldn't show that graph if we wouldn't look quite good with the part that I just described you. It's here. So we want to have a large load current range for minimum to maximum and high efficiencies over here at the right. But in addition, we have a color code. The color code shows how much is the voltage range that we support here. And our part was also intended to support the full lithium-ion battery voltage range. So, and we achieve good efficiency if we use partly external components. We also investigated that we can even go close to 90% efficiency. The load current ranges from 0.5 milliamp in low power mode up to 125 milliamp. So there's a lot of work ongoing in that field to increase efficiency, load current, and other parameters. Now you may say there is 85% is not so much compared to more than 95% that we could achieve with switch mode conversion, and that's true. But if we do a little calculation here for a smartwatch, iWatch, which draws roughly 100 milliwatts here, our solution with such a fully integrated power management would 85% efficiency would lead to battery times of 8 hours, while a conventional linear regulator, which would roughly have 50% efficiency, would show roughly half of the battery time. So it's quite conservative. It's actually 4-point-something hours in battery time. Just to give you a little bit indication that this is already a lot running at 85%. So with that, let me spend the last few minutes on the large field of power electronics, which is nowadays seeing a lot of activity. And the goal also here is to come to compact and efficient solutions. So we talked already about the automotive space. We talked about a little bit data centers, smartphones, industrial. So the key component here is the power stage consisting of power transistors. So they can be in higher power, in the higher power domain, they can be discrete components as shown here, or we can integrate those power stages on the die with very nice characteristics. We can achieve 100 milliohms of on resistance on chip, along with currents that are in the few amps range. And this is really great voltages up to 100 volts, and in dedicated processes even higher. But nevertheless, in the end, it's always power switches that we need to drive here. And for power electronics, usually it's a discrete device. So, and in particular, nowadays we see a new class of semiconductor material, which is gallium nitride, which allows to even further scale down our power electronics in size and achieve higher efficiencies. And this is because it requires much lower energy to turn the transistor on and off. So how does this look like? We have a the gallium nitride device here connected to a gate driver, and the gate driver is controlled by bringing gate charge onto the gate or by withdrawing the charge so that we turn off the device. And now if you compare such a state-of-the-art GaN transistor with a conventional high voltage silicon device, we identify that the control voltage is roughly 10 volts in the silicon case, while it is typically 5 volts for GaN. Also, our threshold voltage is smaller, and this is the main point, our gate charge is a factor of 10, roughly smaller for GaN with similar characteristics. And that's the key reason why we benefit so much from gallium nitride. So and then the question comes up, how can we benefit also on the circuit side? And so we looked at the gate driver implementation in particular. So let's look at it on this slide here. Where does the gate charge come from? In the conventional power electronics, we apply a external capacitor that delivers the charge that goes onto the gate through the gate driver. And now, knowing that our power electronics, that our GaN in power electronics would take just 10 times lower gate charge, we could really think of integrating the capacitance or the capacitor on chip to get rid of a lot of connections, interconnections, parasitics, and get also the board space smaller. So again, a trend to get rid of discretes at the PCB level. So now this is the simple equation. If we have a given gate charge, we simply allow a certain drop at the capacitor, and that allows us to calculate the capacitor value. Now in this example, let's take a typical value for GaN, which is 10 nanocoulombs, and we allow ourselves a drop of 100 millivolts across the capacitor. That gives a capacitance value of greater than 100 nanofarads. So this is a lot, and we all know in microelectronics this usually could not be integrated on chip. It's still too large, even though we use these advanced gallium nitride components. So what did we do? We came up with the idea that we called high voltage energy storing. The idea is quite simple. We increase the voltage swing, and by doing so, we can decrease the capacitor. So in the end, conventionally, we would drive with 5 volts, our GaN device with 5 volts. What we do here is we charge the capacitor to 15 volts, and then we dump all this 15 volts onto the gate of the transistor, and due to the charge sharing, it goes down to 5 volts. Sounds a little bit scary, but it works very well. And since we increase the swing significantly here, delta VC, we can decrease the capacitor value by the same amount, and that can be integrated. So we end up in values which are below 1 nanofarads, and that can be integrated on chip. What we did here in this case, we even implemented a resonant tank here by adding an inductor in the charging path. So again, we have a resonating behavior which increases efficiency and allows to fully discharge the capacitor and still deliver the proper gate charge. And in the end, we can deliver significant gate charge out of this on-chip capacitor. And that's what we showed at ISSCC 2017. We achieve 11 nanocoulombs, which is sufficient to supply practically all commercially available GaN devices. So, and that without any external component. So I'd like to show you the implementation here, because this is usually quite nice. To implement this high voltage energy storing, we benefited from stacking different capacitor layers, and on top we placed a spiral inductor of 40 nanohenries. So that's all here on the IC. A little bit the test setup with a lot of connecting bond wires for testing. And that's just to show you how it in the end looks like here. It's reasonable in size. That shows one of the benefits of gallium nitride to contribute to smaller solutions in power management. But gallium nitride is really exciting. It also is a lateral device, which allows to integrate also analog circuits besides the power device, and that brings us to monolithic GaN integration. So this is really a new trend. There are few process technologies available nowadays that allow a full monolithic integration based on GaN. And what we presented at this year's ISSCC is one of the first complex GaN ICs. This is the IC here. And what we do here is it's an offline buck converter, which delivers 15 watts, and it's a 400 volt because it's an offline. It handles 400 volts. So this is a little bit a block diagram. We have our rectifier implemented here, EMI filter, and then we go into this LC filter we see again here. And we have a LED string attached to it to show the operation as an LED driver. But it is not necessary to run it really as an LED driver. Basically, it's a step-down converter. So, and this is our GaN die, which comprises a power transistor. It's a GaN transistor, which is capable of 650 volts. And then we have a control loop implemented here with analog circuits also in GaN. And this is the first IC that really has a closed loop control implemented. And with the benefits of GaN, we achieved the highest peak efficiency compared to a previous prior art fully integrated power stages. Component count is low and also small, and so we achieve 44 watts per cubic inch power density in this case. So it's really exciting. That's a lot of fun, and we continue on that topic. So now we are almost done. Watching the time a little bit. On the wish list of power electronics designers, one of the top items is current sensing, and in particular wide bandgap current sensing. So commercial solutions are usually too slow, too expensive, and too bulky. And so we investigated the concept of Rogowski call sensing on IC level. So the idea is to place an IC on top of a copper metallization of a power module and to detect the current by means of the electromagnetic field. And this coil here takes the magnetic field, and as this is an AC coupling, we benefit from the better coupling, which increases over frequency. So it's really, really well suitable for high frequency current measurement or current sensing, but it of course doesn't work at DC. So for DC, we have implemented a Hall sensor, and then we combine both to a hybrid sensor, and that allows us to really sense in between DC and 75 megahertz, which is really a lot, and that even allows to sense the current waveforms in motor control in real time. So it's a lot of nice applications. This is how it looks like in the test setup. And this is actually something which could be interesting if someone is interested to commercialize that. I would be happy to talk to you, because this is now open research, but it has a lot of potential also to bring that towards a product. So, and there's no talk nowadays without artificial intelligence. I have one slide on AI related to power management. So if you look at our human brain, it's really magical what we can do with a few watts of power, right? The brain takes 20 watts. And if we want to replace that by an AI implementation, there are various studies that calculate how much computing power you need to do that. I'm citing here a study of IBM. And if you then calculate the power, it accounts to 6 megawatts. And that's a lot, right? We can operate a whole semiconductor fab from that, or we can run a high-speed train or a small town. So of course, we will never completely, or at least not medium term, we will not completely copy a human brain. We will only implement partial functions of it. But still, this example, I feel, indicates nicely how power management is an enabler for AI computing. So I wanted to highlight that. So there's a lot of things to do, and that also brings me towards the end of the talk. So let me summarize. This is again our scheme and power management, and key care abouts are size, efficiency. Then we have some disturbances caused by the switching nature of power conversion. And of course, cost needs to be low, that's clear. And in the end, it's still a lot of fun. Hopefully, I could demonstrate that. We see a trend towards higher voltages on the input side, and we see at the electronics, of course, lower voltages, wider load range. So I really hope that I could share some excitement about power electronics with you, power management. I also would like to thank the Solid State Circuit Society of the IEEE to also co-organize this whole event. And of course, I have to thank my research staff. Without their engaged and dedicated work, it would not be possible to show you all the nice results today. But I also want to like to thank you, of course, for listening and joining this talk. Finally, I also provided some references so which you can refer to later on. That ends my talk. Thank you very much.
Thank you very much, Bernhard. It was very interesting and exciting. I suggest that the questions will be by raising your hands, by pressing the button. Other questions?
So I saw already in the chat there is a request, do we get the slides? Yes, this is for sure you can get the slides, and perhaps you can also access the video as it was recorded.
Yes, the video was recorded and we'll send the link. Okay, so if there are no more questions, then thank you very much, and we hope to see you soon in Israel and to give even a longer course. It will be excellent.
Shachar?
Yes.
Shachar, just a second. Somebody asked to unmute, and there was also a question in the chat. So I think somebody asked to be unmuted. Who?
Yeah, I see Matan. I see that Matanti asked the question, right? Yeah.
There's one question. I'm spotting the question. How does SiC compare to GaN on efficiency? I think that's one question we can maybe talk about. Even though I have to say I'm not a SiC expert, because this is really also maybe the different application space in between SiC and GaN. So SiC is more to replace IGBTs in the higher voltage space, while GaN is more like 600 volts and below. And so that's why it's difficult to compare. In the high voltage space, SiC definitely would also enable efficiency benefits that we see here for GaN in comparison to silicon-based devices. So probably that's just a high-level answer. So that's a little bit out of my let's say voltage space that I'm looking at.
Okay, and there is a question by Yossi, right? Yossi Shaw.
Yeah. So hi, Bernhard. Thank you very much. Very interesting. I was curious about this GaN circuits. Are the circuits gallium nitride, or they're silicon with the GaN?
Oh yeah, great. Thanks for asking this question. So in fact, it's really gallium nitride. So I try to go back real quick. So this is the exciting thing. So all these circuits are really gallium nitride. So in this gallium nitride technology, so you have a high voltage device available, and we have also low voltage devices like regular N-type transistors, which have 20 volts, I think, as voltage max ratings. And then we have available resistors and capacitors, and basically that's all. With that, we need to live with it, but this is all in GaN.
Is it GaN on silicon, or is it bulk GaN?
Yes, it's GaN on silicon, yeah.
And manufactured by Cree or other companies?
Yeah, I can't talk about that under NDA.
Okay.
Unfortunately, this is such a new technology. Then most people probably they're all under NDA. Sorry for that.
Sure, I understand.
Yeah. But it's what is interesting here is that since we do not have a p-type device, so there's no p-type device available in GaN, and that's interesting. So it brings us back to the 1970s when we didn't have CMOS, we had just N-type plus resistive load, right? And so that's the challenge. How do we build good analog circuits and even logic with the only N-type only implementation? So we really had to look up old publications from the 70s to benefit from it. And of course, we came also up with some new ideas, which are partially in that paper.
That's very cool. I'll definitely look up the paper. Thank you.
It's fun. It's really fun. Thanks for the question.
Moshe, do you have a question?
Yes, yeah,
Okay.
Okay.
all the integrated inductors in the eye are core free, are not material magnetics.
It's
Integrated
no magnetics.
Yeah.
So we have not used any magnetics in anything I've shown here. All the things, they are just air-core inductors. Of course, we are limited in Q factor here. For instance, the variables, and the variables, we have measured the Q here. Where is it? Here. This guy here has this inductor here has a Q of 6. So it's not much, but already it allows us to bring up the efficiency significantly compared to a conventional switch cap implementation.
Thank you. Another question is,
some more question. How do you have some experience then in the temperature changing and how the delay can adapt to all the changing temperature? One of the question. And the second, if your load are not constant, they are changing very fastly, and the different loads can be adapted. The circuit, the control loop can be adapted to that.
Yes, so maybe I answer your first question first, your last question first. So we have implemented a control loop here, which is extremely fast. So we have very fast response times. We measured it all with with various load steps and varying input voltage and so on. So that works actually quite well, and that's probably the answer also how we can handle temperature changes. So the control loop is something what we do is, one of the elements is we change the switch conductance of all these switches, and that allows us basically to damp our resonant behavior. That's usually lossy, but it allows us to stay at a reasonable frequency so that our losses are still kind of optimized. So that's something also we show. We have implemented that control loop and showed it at this year's APEC, which actually didn't take place, of course, but this is the, there we have described all the control features that we have implemented here. But it's for sure we need to have a high-speed control. We have a coarse and a fast response loop and all these things, but still it's not too complex, I would say.
Okay.
thank you.
Yeah.
Excellent.
Yeah, I wanted to keep that reasonable in length. Otherwise, I could show you also some measurements of the control loop behavior here, responses and so on. I think that's nicely doable.
Okay, excellent.
Yeah, sure. You're welcome.
Cheers. Very nice.
Just thank you, amazing.
Yeah, thank you. Hope it was really interesting.
Another question for the future.
Okay. Any other more questions? if not, thank you again and hope to see you soon.
Yeah, the pleasure was on my side. So have a good afternoon or evening. Yeah, so if you have any further questions, feel free to email me. That's also fine. Thanks a lot.
Thank you.
Bye-bye.